So, hello everyone. As was said, my name is Christoph and our paper is called Common Bugs in Scratch Programs. So, Scratch is a programming language for introducing students to programming, where you program sprites on the stage by assembling blocks like these. And there are some fairly sophisticated programs even for students. This snippet was taken from a game where the programmer wanted to allow the user to enter a Hall of Fame if he or she reached the 21st level. But if you take a closer look here, you can actually see that we compare the string level with a number 21. So what this means is that, of course, this will always be false, and the if block is never executed, and no one can actually enter the Hall of Fame in this game. And this must be fairly frustrating for the programmer or for the player. And it means that simply the game does not work as intended. And it can also indicate that there are some misconceptions the student has about how to use variables or what strings versus numbers are. So when we look at things like this, our goal was to detect bugs like this automatically, to help students debug their programs and, well, increase the fun for the programmers, and also detect such misconceptions, and also for teachers maybe to evaluate the programs. And if we look again at this example, we can actually see a pattern here. So if you have a comparison in an if block, and you have two literals that you compare, you will always get a constant true or false value, which indicates that there is something wrong. So the if is either unnecessary or there is a bug because the if branches may never be executed because of the constant false value or true value. Another example of where we can find patterns like these is when we look at custom blocks. So custom blocks are similar to functions or methods in other languages, where you can assemble some blocks together and give the custom block a name, and also provide parameters to the block and give the parameters names. But as you can see here, the parameters do not have to have different names, or in fact, do not have to have names at all. So this means that the pattern here is that if we have a custom block with multiple parameters, and the parameters have the same value, same name, some of them, that some of the parameters cannot be used. So only the first parameter with this name can actually be used in the custom block, which means that the custom block may not be working as it's intended by the programmer. And as a last example, to focus on Scratch working on the stage, here we have a snippet with the popular pen extension. So here we have a block which leads the sprite to go to the position of the mouse. And then whenever the player presses the mouse down, the pen is lowered onto the stage and starts to draw. And when the mouse is released, the pen is lifted again and stops drawing. But as you can see in the snippet, there's actually no block about erasing anything. So the pattern here is that whenever we have a pen down block and there is no erase all, what this leads to is that you can draw on the stage, but you can never get rid of what you drew before. So even if the program is restarted, the drawing remains, forcing the user to reload the Scratch page. So when we look at those examples, what we came up with is a catalog of 25 of these bug patterns. And when we analyzed them, we found that you can actually put them into three categories. So the first category are what we call general bugs. So these are bugs that can happen in most programming languages, like when we compare literals. And the second category with the parameter names or similar bug patterns are what we consider syntax errors. So in most programming languages, a compiler or an interpreter would actually catch this and prevent the programmer from making this mistake. And the third category are what we call Scratch-specific bugs. So these are bugs that can happen because Scratch uses sprites and is working on a stage. So To come closer to our goal of finding these bugs automatically, we implemented a tool called Litterbox. Litterbox takes a Scratch project or its ID and downloads the project, and it contains the 25 bug patterns and then analyzes the Scratch project. And if it finds code that corresponds to one of the bug patterns, it flags the project and tells the user that there is a bug. To evaluate this, we assembled a data set with around 135,000 Scratch projects over a period of 3 weeks. And we excluded remixes to make sure that if we find a bug, that it's actually a bug created by the program of the project and not that it was inherited by some parent project. So around 75,000 project remains. And what we then found is that in this data set, we found around 110,000 bugs in total and 33,000, so around 45% of all the projects contained at least one bug. And of those, the most common bug is what we call stuttering movement. So stuttering movement is when you try to change the position of a sprite by using key presses, but since the key press signal is only sent with a delay to Scratch, the sprites tend to stutter instead of moving fluently, which can be fairly annoying if you play a game. The second most common is what we call a message never received bug. So you send a message and expect that there is some other code that is waiting for the message and then responds to it. So here we have a message called game over. We broadcast this message, and then of course we expect that some other part of the program actually stops the game. But if this message is never received, nothing happens. And corresponding to this is the opposite, where we have a message never sent bug. So this was taken from a game where there was a dog, and the dog was waiting for a message woof. And when the message was received, the dog was barking. But if the message was never sent in the first place, the dog couldn't do what it was supposed to do, so it was simply just a dead sprite. So after looking at these bug patterns in our catalog, we wondered how severe is the impact actually in real programs. So we manually analyzed 250 projects, so 10 projects per bug pattern. And what we found is that of these 250 projects, 70 contained a bug which led to a failure. So this means that the project did not work as intended, or in some cases even stopped working completely. In 96 projects, there was no visible impact. Maybe sometimes because the sprite where the bug was contained was hidden, or because it was off screen. And in 52 projects, the bug was in dead code and was simply never executed. All three of these categories are interesting for students because, well, in the first category, of course, there's a failure. And in the other two categories, we might see a failure as soon as the program is changed. So when the sprite is becoming visible, or if the code is executed, we still might break the program. And only in 32 cases did we see a false positive. Well, that's already it. So to sum it up, we saw that we can abstract from a given bug and find a pattern. And we showed a catalog of 25 of these bug patterns and categorized them into the general bugs, into syntax errors, and Scratch-specific bugs. And we implemented a tool, Litterbox, to automatically analyze and detect these bugs in Scratch projects. And we analyzed these in a real data set and showed that these bugs actually do occur and in a lot of cases actually do cause problems. Litterbox itself is available as open source on GitHub, so you can download it and analyze your own Scratch project. That's it, and thank you for your attention.